So let's review section 4.1. Right, we don't get into logarithms quite yet. Okay, we just review exponential functions. Okay. So if a is a real number and n and m are positive and have no common factors, then a to the m over n power, right? M over n is the exponent, right? A raised to the m over n power can be written as, is equivalent to a raised to the m power, and then we take the nth root of a to the m power. Okay? Now equivalently, you can reverse the order. You can take the nth root of a and then raise that quantity to the mth power. In simplifying a to the m over n power, okay, it's often you can do the math in your head by taking the nth root of a first and then raising that result to the nth power, instead of raising a to the nth power and then taking the nth root. Okay. So I say m over n power, but this fraction in the exponent, okay, we call m the power, and we call n the root. So let me do it this way. So a to the m over n, m is the power, and n is the root. So it really helps to be on time. Okay, because you interrupt class every time you do this. Okay. So the rules of properties of exponents, aerodynamic properties of exponents. So if I have b raised to the mth power, okay, this is called an exponential. B is the base of the exponential. And m is the exponent of the exponential. Okay. So in the arithmetic properties of exponents, I have a product of two exponentials with the same base. So in simplifying, right, we just add the exponents. In 2, we're dividing two exponentials with the same base. And so we just subtract the bottom exponent from the top exponent in simplifying. And you know that b raised to the minus m power, the minus sign of the exponent means reciprocal. So this is 1 over b to the m. And in 4, we have b to the m. We have an exponential raised to another power. And when you raise an exponential to another power, you just multiply the exponents. In 5, we have a product raised to the mth power, and that's equivalent to the first factor raised to the mth power times the second factor raised to the mth power. And then in 6, we have a fraction raised to the mth power, and that's equivalent to the numerator raised to the nth power divided by the denominator raised to the nth power. Okay. So in example 1, right, we're going to simplify some exponentials. So in the first case, we have the fraction 8/27 raised to the 1/3 power. And so by property 6 here, okay, that is equivalent to the numerator raised to the 1/3 power over the denominator raised to the 1/3 power. Well, you know, anything raised to the 1/3 power means cube root. So we have the cube root of 8 over the cube root of 27. And the cube root of 8 is 2. And the cube root of 27 is 3. Any questions on that? In B, we have 9 raised to the 5/2 power. Now, as I was pointing out, they're written on the board, right? A raised to the m over n power, right? You can raise a to the m power and then take the nth root, or you can take the nth root of a and then raise that result to the mth power, right? You get to choose what order, okay? Well, we could raise 9 to the 5th power, but what's 9 to the 5th power? Can you do that in your head? Right. But instead, we can take 9, right? A root of 2 means square root, right? A root of 2 means square root. We take the square root of 9 and then raise the result to the 5th power. To do 9, taking the square root of 9 to the 5th, we raise the square root of 9 to the 5th power. Well, square root of 9 is 3, and 3 to the 5th is 243. That you can do in your head. Okay. In C, we have 27 raised to the minus 2/3 power. Okay. Well, you know, a base raised to a negative power, right, means reciprocal. So we can write this as 1 over 27 to the plus 2/3 power. Now again, I could square the 27 and then take the cube root, but what's 27 squared? Can you do that in your head? No. But we could take the cube root of 27 first, and then square the result. And the cube root of 27, you know, is 3. So this is 1 over 3 squared. And that's equal to 1/9. Okay? So that's application, right, of the rules of exponents. Okay? Any questions on that? All right, exponential function. The exponential function f with base a The exponential function f with base a is denoted by f of x equals a to the x, where a is a positive number and not equal to 0. And x is, right, the variable x is any real number. Okay. The number a is called the base, and x is called the exponent, right? And that makes sense, right? This is an exponential, a to the x, a is the base, x is the exponent. Okay. A has to be a positive number, not equal to 0, and x can be any real number. In example 2, we're going to graph each of the given functions. So the first one we're going to graph is f of x equals 2 to the x. And I have provided you with a grid. And so here's the grid that I provided you with. And f of 0, right? The value of the function x equals 0 is equal to 2 to the 0. 2 to the 0 is equal to 1. So the point 0, 1 is on the graph of this function. Okay. At x equals 3, f of 3 is equal to 2q. Right? So the value of the function x equals 3 is equal to 2q, which is equal to 8. And so the point 38 is on the graph. F of minus 3 is equal to 2 to the minus 3 power. And you know 2 to the minus 3 is the same as 1 over 2 cubed, which is equal to 1/8. And so the point minus 3, 1/8 is on the graph. Okay. So let's plot those 3 points. So the point 38 is on the graph, which is up here. The point 0, 1 is on the graph, which is down here. And the point minus 3, 1/8 is on the graph, which is just above the x-axis right here. Okay. So here's the point minus 3, 1/8. Here's the point 0, 1. Right, that's the y-intercept. And here's the point 38. And so when you connect the dots with a smooth curve, see that the graph of this exponential function looks like that. Any questions on that? So if you flip your document over, your handout over, we're going to graph the function f of x is equal to 2 to the minus x power. Okay. Well, you notice that the difference between these two functions is that x has been replaced with minus x. And when we study transformations of functions, what happens when you replace x with minus x to the graph? What does it do? How does it affect the graph?
Across the
Y-axis, right? Flips it across, reflects it across the y-axis. So in graphing 2 to the minus x, we just got to flip this graph across the y-axis, right? So this point goes from here over to here. The y-intercept stays in the same place. And this point goes from here over to here. Well, 2 to the minus x is the same as 1 over 2 to the plus x, right? From the rules of exponents. And 1 over 2 to the x is the same as 1/2 to the x power. So over here, the base is greater than 1, and over here, the base is between 0 and 1. Okay? And so what we're going to find is when the base is greater than 1, the graph goes up and to the right like this, and when the base is between 0 and 1, it goes down to the right. Flip over. So let's graph. I've provided you with a grid. And so, and you can plug in 0 in for x, right? 3 in for x, -3 in for x, right? To verify that these points are correct. And so this point here goes from 3, 8 to -3, 8. And we still have the x-intercept, or the y-intercept at 1. And then this point at -3, 1/8 comes over here to 3 plus 1/8. And so the graph comes down and flattens out to the right, right above the x-axis. Okay. So all we did was reflect f of x equals 2 to the plus x across the y-axis. Any questions on that? All right. So in general, okay, the graph of f of x equals a dx where a is greater than 1, right? The graph goes up and to the right, crossing the y-axis at y equals 1, like in this example over here, where a is equal to 2. And notice in this case, a is equal to 2, which is greater than 1. Okay. So whenever the base is greater than 1, okay, a to the x, the graph a to the x will go up and to the right like this. Okay. And when the base is between 0 and 1, right, when a is a positive fraction, right, between 0 and 1, then the graph of f of x equals a dx will go down and to the right, like this graph over here. Okay. In this case, a is equal to 1/2, which is between 0 and 1. Now, in both these situations, the domain is all real numbers, right? You can put in any real number in for x up here in these functions. The range, you can see, well, let's point out first what the horizontal asymptote, right? Both these graphs have a horizontal asymptote, right? Up here, it flattens out going to the left, right above the x-axis, which is the horizontal line y equals 0. And here it flattens out going to the right, right above the x-axis. Remember, the horizontal line y equals 0 and the x-axis are coincide. So the range, all the y coordinates are greater than 0. So the range is from 0 to infinity, right? With parentheses around the 0, right? Y is greater than 0. So we could write it this way, right? That y is greater than 0 in both those cases. And in both cases, right, when you put 0 in, you evaluate the function x equals 0, you get f of 0 is equal to 1, right? So the y-intercept in both those cases is y equals 1, or the point 0, 1. And then we already know about the horizontal asymptote. Okay. So in the example down below, we're going to graph two exponential functions that have been transformed. Right? So f of x equals 3 to the x plus 1 is a transformed exponential function. And this is a transformed exponential function. Okay. And so we're going to graph both of those. So we have f of x is equal to 3 to the x plus 1 power. Okay. Now, if I have g of x is equal to 3 to the x power, okay, and I replace x with x plus 1, we know what the graph of g of x looks like. Okay. It goes up and to the right, crossing the y-axis at y equals 1, right? When I replace x with x plus 1, what happens to this graph? Right, that's a transformation. How does it get moved? How does it get shifted? Is it up? To the left, right? When you place x with x plus 1, it shifts the graph to the left. And how far does it shift it to the left? 1 unit, right? So the y-intercept here now gets shifted to the left 1 unit, right? So this y-intercept that's at 0, 1, when it gets shifted to the left 1 unit, right, it's going to be at minus 1, 1. Okay. So there's a little bit of a grid there, coordinate plane provided for you guys. So the y-intercept was at 0, 1. Now it's at that point that crossed the y-axis, now at minus 1, 1. Okay. So this function is going to have a new y-intercept now, right? So f of 0, right? Remember the y-intercept is equal to f of 0, and f of 0 in this case is 3 to the 0 plus 1 power, which is equal to 3 to the first power, right, which is just 3. So the y-intercept now is, right, it is y equals 3, right? This graph crosses the y-axis at y equals 3. So 0, 3 is the y-intercept. So this graph over here just gets shifted to the left 1 unit. So it goes through the point minus 1, 1, and it crosses the y-axis at 0, 3. So graph of f of x equals 3 to x plus 1 is the graph of 3 to the x shifted to the left 1 unit. All right. Next, we're in B, we're going to graph g of x equal to 1/4 to the x power minus 1. Okay. So we know what the graph of f of x equal to the x to the 1/4 power looks like. goes down and to the right. Right? That's what we learned right up here. Okay? So A in this case, right, is equal to 1/4, which is between 0 and 1. So the graph looks like that. Crosses the y-axis at y equals 1. The x-axis, sort of the horizontal line, y equals 0, is a horizontal asymptote. So, oh man, I wrote that backwards. Sorry about that. Nobody said anything. This is 1/4 to the x, not x to the 1/4. That makes a big difference. Okay. Right. Okay. So 1/4 to the x, right? That graph goes down and to the right, crosses the y-axis at y equals 1. X-axis is the horizontal asymptote. Okay. Now, if I subtract 1 from the right-hand side, right, to get the function g of x, the graph of g of x is the graph of f of x shifted how?
Down 1.
Down 1, yeah. So when we subtract 1 from the right-hand side, it shifts the graph down 1 unit. So y equals 0 is no longer the horizontal asymptote. When you go down 1 unit, the horizontal asymptote is now y equals -1. Okay. This graph flattens out to the right, right above the horizontal line, y equals -1. This is the horizontal line, y equals -1. Well, when we shift this graph down 1 unit, the y-intercept is going to get shifted down 1 unit, right? To what point? Yeah, the origin. So now the y-intercept is at the origin, okay? And so the graph comes down, crosses, goes through the origin, and flattens out to the right, right above the horizontal line, y equals -1. So the y-intercept is now at y equals 0, the origin, and y equals -1, right, is the horizontal asymptote. Any questions on that? Yes, sir.
How did you get the origin to the y-intercept?
Oh, well, the y-intercept over here is the point 0, 1.
Oh.
So when you shift it down 1 unit, subtract 1 from the y-coordinate, you get 0, 0. Yeah. Yeah. All right. Any questions on that? Okay. All right, so if you flip over to page 3, we're going to learn about the natural exponential function. Okay. And, right, you guys know about special numbers in mathematics, right? We've been working with I, right, the imaginary number I. You know about, probably know about pi from trigonometry. Well, there's another special number in mathematics with its own name, and that's the number e. And that's really a fascinating number. Okay. So how the number e comes about is we have this sequence of numbers generated by this formula, 1 plus 1 over n to the nth power. And so, you know how a sequence of numbers works, right? The first number in the sequence, you put in 1 for n. For the second number, you put in 2 for n. The third number, you put in 3 for n. For the 100th number, you put 100 in for n, and so forth. And so over here, I have a table of values. So in this sequence of numbers, when the first number, n equals 1,
right? You plug in 1 in for n, you get 2, right? So the first number in the sequence is 2. When you put 2 in for n, you get the second number in the sequence is 2.25. When you put 100 in for n, the 100th number in the sequence is 2.7. When you put 1,000 in for n, the 1,000th number in the sequence is 2.717. And when you put 10,000 in for n, the 10,000th number in the sequence is 2.718. And you can see that as n gets larger, the sequence of numbers, right, isn't going to infinity. It's getting closer and closer and closer to a particular number on the real number line. And it's this number to 5 decimal places, 2.71828. It's sort of it's fascinating that, for me, that as n gets larger and larger and larger, the sequence of numbers gets closer and closer to this one particular number on the real number line. And that's the number here. So in fancy mathematical notation, we have 1 plus 1 over n to the n approaches 2.71828 as n increases without bound, right? As n goes to infinity. And so, because of this special number, it gets its own name, and we named it E. Mathematicians way back when named it E. And E, the number E is greater than 0. It's not equal to 1. So, in our notation for an exponential function, right, our notation for the exponential function is f of x equals a to the x. Well, and a has to be greater than 0, not equal to 1. Well, e is greater than 0, not equal to 1. So when we put e in for a, we have e to the x. And that is, that exponential function has its own name, fancy name. It's called the natural exponential function. So whenever you hear talk about the natural exponential function, we're talking about the number e raised to the x power. Okay. Functions like 3 to the x and 1/4 the x, right? They don't have their own names, but e to the x does, right? Because it's this fancy number, right? This sort of this miracle number from mathematics. Okay. So in example 4, right, we graph the function e to the x, and since e is greater than 1, right, its graph looks like 3 to the x, right, goes up and to the right, from left to right, and it crosses the y-axis, right, at y equals 1. Y equals 1 is the y-intercept, and the horizontal line y equals 0, right, is a horizontal asymptote. Okay. So this is what it looks like for, right, this is what the graph basically looks like for any exponential function where the base is greater than 1. Okay. In B, we are graphing a transformation of e to the x, and how I know it's the graph goes down and to the right. We start off with y equals e to the x, and then if we replace x with e to the minus x, right? So the graph starts up going up and to the right, and then we replace x with e to the minus x. It goes down now to the right, right? Gets flipped over the x-axis. And then if we replace x with x plus 1, or excuse me, replace x with x minus 1, then we have the negative of x minus 1, right? So first I replace x with minus x, and then I replace x with x minus 1, so I have e to the minus x minus 1. And you know when you replace x with x minus 1, it shifts the graph to the right 1 unit. So here it's crossing the y-axis at y equals 1. And now this y-intercept gets shifted to the right. Now we have a new y-intercept up here somewhere. So this point, y-intercept at 0, 1, is now at 1, 1. Okay. And where it crosses the y-axis is at the number e raised to the first power, okay, which is 2.718. Okay. So to get this graph, right, I took the graph of e to the x, reflected it across the y-axis, and then shifted it to the right one. Okay. Now that's all back from transformations, right? When we did transformations in chapter 2. Okay. All right. So any questions on that? All right. In the example down below, right? The exercise down below, we're going to find an exponential function of the form f of x equals b to the x, such that the graph of f passes through the point 2, 9. So the point 2, 9, right? The x coordinate is 2. And the y coordinate is 9. Okay. All right. So f of x is equal to b to the x, and it passes through the point 2, 9, right? The graph of our function passes through the point 2, 9. X is equal to 2, y is equal to 9. Well, you know, y values and function values, right? They're the same thing. So replace f of x with y. And this graph of this equation has to go through this point. So I put in 9 in for y and 2 in for x. So I have 9 is equal to b squared. And now I solve for b. So b squared is equal to 9. And then, you know, square root on the squaring. Now, usually when we use the square root method, we put plus or minus in front of the square root. Does anybody know why I didn't put plus or minus in front of the square root this time? Because the base has to be positive, right? B has to be greater than 0 and not equal to 1. So we have B is equal to plus 3. So now I replace B up here with plus 3, and we have the exponential function for this problem. F of x is equal to 3dx. And you can see it satisfies this requirement, because when I put in 2 for x, I get 3 squared, which is equal to 9. Any questions on that? All right. One-to-one property of exponential functions. Okay. For a greater than 0, not equal to 1, right? So we have 2 exponentials that are equal to each other with the same base. And if we have 2 exponentials equal to each other with the same base, then it has to be true that the exponents are equal. And so we have a to the x to the 1 is equal to a to the x to the 2. The base is a for both exponential, so it has to be true that the exponent x1 equals the exponent x2. So we can take advantage of that property in solving some exponential equations. 27 to the x minus 1 power is equal to 9 raised to the 2x minus 3 power. Okay. Now, exponential on the left equals exponential on the right, but they're not the same base. So we can't just set this exponent equal to that exponent and solve for x. But we can rewrite both exponentials with common base. You know that 3 cubed is equal to 27, and 3 squared is equal to 9. So we replace 27 with 3 cubed, and we replace 9 with 3 squared. And I gotta put the 3 cubed in parentheses, right? Because it's 27 raised to x minus 1. So it's 3 cubed raised to the x minus 1. Likewise, it's 9 raised to the 2x minus 3. So it's 3 squared raised to the 2x minus 3. And now we can use property 4 from page 1, the arithmetic properties of exponents, to simplify the left and the right hand side. So on the left side, right, we have a base raised to a power, that quantity raised to another power. So by property 4, that's equal to 3 raised to the 3 times x minus 1 power. Right? We multiply the exponents. And we do the same thing on the right hand side. We multiply the exponents. We have 2 times 2x minus 3. Now we have an exponential on the left equals an exponential on the right. They have the same base. Okay? And so by the one-to-one property, page 4, this exponent must equal that exponent. Okay? That's what the one-to-one property says. We have an exponential on the left equals an exponential on the right, but they both have the same base, so the exponents have to be equal. So we have 3 times x minus 1 has to equal 2 times 2x minus 3. So we distribute the 3 on the left. We have 3x minus 3. We distribute the 2 on the right. We have 4x minus 6. Now you just solve for x, right? We're solving for x. So we move the 4x to the left via subtraction. We move the minus 3 to the right by addition. 3x minus 4x is minus x. And minus 6 plus 3 is negative 3. And then when you divide both sides by negative 1, you get x is equal to plus 3. So, you put 3 in for x up here. 3 minus 1 is 2. So we have 27 squared is equal to, and on the right, put 3 in for x. If 2 times 3 is 6, and 6 minus 3 is 3. So you can verify with your calculator that 27 squared and 9 cubed are the same number. Okay. Any questions on that? Okay. All right. In B, we have 4 raised to the x squared power is equal to 2 raised to the 3x plus 2 power. Different bases. So we can't use the one-to-one property yet. But you know that 2 squared is equal to 4. So we're going to replace 4 here with 2 squared. We have 2 squared raised to the x squared power is equal to 2 raised to the 3x plus 2 power. And now, right, by property 4 from page 1, on the left-hand side, we can multiply the exponents. And we have 2 raised to the 2 to the x squared power is equal to 2 raised to 3x plus 2. And now we can, using the one-to-one property, we can equate the exponents. Okay. Hold it. You guys let me get away with bad math. When I multiply these exponents, we get 2x squared. Right. This is 2 times x squared. So now the exponent on the left, 2x squared, is equal to the exponent on the right, 3x plus 2. And now this is a quadratic, okay? We're going to have to factor. So we'll put it in standard form by subtracting 3x and 2 from both sides. You get 2x squared minus 3x minus 2 is equal to 0. What does that factor to? What are the numbers? 2x, what goes after 2x? Anybody know? Plus 1. What goes after the x? Minus 2, right? We have 2x plus 1 times x minus 2. So either the first factor is equal to 0, or the second factor is equal to 0 by the zero product property. And we get x is equal to minus 1/2, and x is equal to 2. So those are the two numbers you can put in for x in our original problem, okay? And the left-hand side will equal the right-hand side. Okay? Any questions on that, ladies and gentlemen? So, we got through this handout.